lab, we're just kind of two parts. Part one is determining the enthalpy or the change in heat of the dissolution of your salt, because everything, one of the key things in science that we want to know is, does it take energy to do something? Does something give off energy? And how much energy does it take in or give off? So to measure that, we use calorimetry. We're going to use a calorimeter, a very basic one, just a piece of styrofoam with a couple holes melted into it. So you can use the same well every time, so that your calorimeter constant should hopefully be consistent for each trial. And you're going to use a different amount of water every trial, so you should be able to calculate the change in energy of the water and the change in energy of your calorimeter. So we've got this equation here: Q-cal plus Q of H2O plus Q of what you're measuring equals 0. So essentially, energy is conserved. It's not created or destroyed, it's just changing forms. So if we're having a log and we burn it, the energy is going from chemical energy to heat plus some other energy in the gas. So it's kind of the same thing when we're dissolving a salt. Some salts give off energy when they dissolve because there's a lot of energy in the crystal lattice, whereas some take energy to dissolve because it has to solubilize the ions. So your Q-cal is just comprised of two terms: the change in energy of your calorimeter, which we just use that as the change in energy of the solution within the calorimeter, times some calorimeter constant, which I believe you'll be calculating today, otherwise it's in your lab notebook. Q of your H2O is sometimes, that's pretty easy to do. We know what the temperature of water that's changing is. We know how much water, so if we use density in milliliters, we can figure out how many grams of water, or we can just weigh the water that we put in. We have change of energy of the water times how much the mass of the water, then times by the constant or the specific heat of water. And the next thing is, the final one is what we're trying to measure. You might see called Q solution, Q dissolution, Q of what you're measuring. This is what you're trying to measure. This is also comprised of a delta T term. That's pretty simple. We need to know how much temperature change. It's comprised of M term, how much mass of what you're trying to measure, how much is being dissolved, how much is being burned, so on and so forth. Then again, a specific heat. We can determine the specific heat, but I think in this lab we're primarily just concerned with the amount of energy, and if that value is plus or minus. Remember that when you set this equation, they're all equal to 0, or you could say that Q measuring is equal to the opposite of these two together if you just rearrange the equation. So I have this delta H, delta T for endo and ectothermic. So if you have something that's endothermic, it's delta H positive or negative. Yes. It takes in heat, so positive. If it's ectothermic, it gives off heat, so it's negative. Traditionally, when you have something that's ectothermic, and you have that solution, and that process is occurring, is the temperature going to go up or down? So that would say that the temperature is going up, and endo, of course, is taking in heat, and the temperature should go down. The second part of this lab is the freezing point curve. Essentially, you're going to take salt, ice, you're going to add salt to ice, and that'll cause the ice to melt, but it won't give off that much heat, and it would cause the ice to get much colder, or the slurry that you're making much colder than what freezing is. Well, much colder than 0 degrees Celsius. That's how people used to make ice cream in the past, which would freeze fairly slowly, but they needed to be able to cause the cream and sugar and everything else to freeze, so they'd add salt to ice around your ice cream maker and stir it, and it would cause it to freeze eventually because they didn't have air conditioners or refrigerator units. Hints that you should know about: use the same well in the calorimeter, like I said, and then use cold DI water when you're trying to get the freezing point curve. There's one characteristic feature of the curve that you should see. It should go down, flatten off, then go down again, but there's something when it's going down before it flattens off that you should see, and if you don't get that, come see me. Today, you guys just need to check out a laptop and temperature probe. So you'll be working with the same groups as you did last week. So I think it's group of 4 again. Another thing is, like I said, use cold DI water for when you're doing your freezing point curve because if you have any ions in your water, you might have seen that characteristic. So that's what you want to see at the beginning of the curve. Finally, what's due today is Lab 10.1 and the pre-lab for 10 Part 2. The pre-lab again, I'm just going to go around initials if you haven't done. Go over to our goggles, and the lab next week is Lab 11, so be prepared to be ready for that. Again, my office hours are at Smith 101J from 5 to 6 p.m. And my email address is dodg0092@umin.edu. If there's any questions,